Hi everyone, in this short video I'm going to talk to you about the so-called nearest-colattice algorithm, which is a way to perform time approximation trade-off for approximate CVP in lattices. So first of all, I'm going to set a bit of setting and talk about lattices, shortest vector problem, and closest vector problem, which are respectively two of the main problems you have on lattices. So in a nutshell, take the Euclidean space here, the Euclidean plane, take a bunch of linearly independent vectors in this space and consider the set of integral linear combination of these vectors. So you get a structure which is very reminiscent of the structure of a grid and which possesses a structure of a subgroup of the ambient space R to the n. So generally speaking, a lattice is nothing more than a discrete subgroup of the Euclidean space R to the n. So lattices are related to many problems in number theory and in geometry, such as to the sphere packing problem, which consists in finding the densest way of packing hard spheres in the space. So here in dimension 2, here in dimension 3. And a fundamental problem in complexity theory related to lattices is the so-called shortest vector problem. It can be defined as follows. I give you a basis of a lattice, any of it, and I will ask you to retrieve one of the shortest vector of the lattice. So you might say, okay, it might be very easy because like I just look at the lattice, look at the 0 vector and take just one of the closest vector to 0. And of course in dimension 2 or 3, it's really easy. You can just look at the grid and say, oh, it's here. But if I give you a really bad basis with very long vectors, such as the yellow one I drew it here, then it will become very hard for you to solve this problem in high dimension. The problem is actually NP-hard in a complexity theory sense. So, of course, you might say if the basis I'm giving you is really good instead, so having short vectors and vectors which are close to be orthogonal to one another, then solving the problem will be easier. And in fact, if I give you a basis consisting of the shortest vectors, then you will just have to give me one of them and it will be done. So as a rule of thumb, I would like to insist on the fact that if you have a very good basis of a lattice, then it will be easy for you to solve your problem on lattices. And I will go back on this intuition a bit later. But first of all, I'm going to move on a second problem, which is the so-called closest vector problem. So if I give you a lattice lambda and a vector t in the ambient space, I will ask you to retrieve the closest vector lying in lambda to the target vector t. So here I draw it in dimension 2, you have this yellow lattice lambda, this target vector t in green, and I will ask you to retrieve the closest vector to t. So here in dimension 2 is pretty easy, of course. But more generally, if I want to know at which distance I will find a lattice vector to my target, then I can compute that by increasing the radius of balls centered on the lattice and wait for them to completely cover the space. And this radius is called the covering distance of the lattice and is denoted by the letter mu. So this would be a fundamental invariant of the lattice, which will be used to see how easy or hard is it to solve our closest vector problem. So we can distinguish two ways of solving the closest vector problem, which is, as the shortest vector problem, a hard problem in complexity theory. On the one hand, we have the enumeration technique, which consists of going down a recursive tree of vectors and to look for close points inside this tree. And the analysis of Enro and Stelle reveals that this technique can be performed in time big O of n power n over 2. On the other hand, we have the sieving procedures, which consist of taking a huge pool of vectors and combine them in clever ways to shrink them iteratively. So we have a huge pool of vectors, and then at the second step we have still a huge pool of vectors which are slightly smaller and slightly smaller, and so on until the right size is reached. So for proved variance of the sieving procedures, we find algorithms which can be solved. We find algorithms which are complexity in 2 to the n roughly, and for heuristic ones, you can solve the problem in something like 4/3 to the n over 2. So this problem is clearly hard, but if you relax it, if you allow not to find the closest vector, but a vector which is approximately close, then the problem is easier as your definition of what is close is relaxed. So formally, we define the gamma approximate CVP problem as the problem of finding a vector v inside the lattice, which is at distance at most gamma times the distance of the closest vector. This trade-off also occurs for the shortest vector problem when you can want to retrieve a short vector, even though not the shortest. So if you want to solve the exact problem, so the approximation factor is equal to 1, then you will have the same kind of technique of enumeration or thieving, and the time you have to spend to solve the problem is exponential in the dimension. But if you allow yourself to solve the problem within a factor beta to the n over 2 beta, for instance, for a parameter beta smaller than n, then you can rely on the so-called big easy algorithm, which solves this problem in time exponentially in beta. And this algorithm hinges on the fact that you can solve the SVP problem in dimension n by some numerous call to the same oracle but in dimension beta, so it's faster in the end. And if you go to the far spectrum of this technique, you retrieve the big easy 2 or LLL algorithm, and you can solve the problem in polynomial time in the input, but the vector you will find is within a factor exponential in the dimension to the shortest vector of the lattice. So this hierarchy of algorithm also exists for approximate CVP by the so-called Canaan's embedding. And this embedding techniques makes you solve the CVP problem you have by calling an SVP problem in dimension n plus 1. So how does it work? If you want, say, to solve CVP in a lattice lambda for a target vector t that you decompose as some error e, which is small, plus a vector v of lambda, then you can retrieve the error e by finding the shortest vector in the lattice of the shape lambda, 0, t, and some constant k that you fix for technical reasons. So since you have a hierarchy of SVP solver in dimension n, then you can apply this hierarchy of polynomial to solve CVP in this dimension through Canaan embedding. But the problem with Canaan's embedding is that, of course, you have this trade-off, that's great, but if I have multiple instances of CVP in the same lattice, then I will maximize as much SVP instances by the embedding technique. And as such, I will have to run the BKT algorithm that number of times. And this is a bit sad because the rule of thumb I gave you earlier, which was if I have a very good basis of my lattice, then I will be able to solve my problem easily, and in particular to solve, let's say, a batch problem when I want to solve multiple instances in the same lattice for a fraction of the cost of what it could take to solve it each time. Then this doesn't work because for each of the target, I have a new full lattice that I have to reduce. So this is kind of unsatisfactory. And what we want to have would be to have a natural approach to the problem which looks similar to the BKZ approach. That means that we would like to solve CVP by calling multiple instances of CVP in smaller dimension. So if we take back this hierarchy I drew earlier, but for CVP this time, what we have currently is that on the one hand, we can solve exactly the closest vector problem using enumeration or thieving, and it costs exponential time. On the other hand, we have an equivalent of this LLL algorithm, which is the nearest plane algorithm of Babai, which solves the closest vector problem with approximation factor exponential. But in the middle, we don't have anything which uses CVP oracles in smaller dimension. And this is exactly where we want to fit our algorithm. So let's see how does this thing work. So let's start with this bye-bye nearest plane algorithm, which is a very fast algorithm, but with very poor quality. So here in dimension 3, what we do is we take sublattice lambda 2 of dimension 2. So here it's in dark gray, and what we do is that we cover the lattice lambda of dimension 3 by copies of lambda 2. So these copies of lambda 2, these cosets, are indexed by the element of the quotient space lambda over lambda 2. So the situation is the one depicted here. We have multiple sheets of copies of lambda 2. So now suppose that I'm taking a target vector t and I want to solve the closest vector problem in the lattice lambda. So what do I do is to look for the closest coset to the vector t, and this closest coset is here in green. And once I've done that, I project my vector t inside this coset v plus lambda 2, and I do a recursion, they call this algorithm back and back, until a closed vector is found. So the cost of this technique is to, on the one hand, solve the closest vector problem in the quotient space lambda over lambda 2, and then the cost of the recursion. So now, if you think of this coset of dimension 2 as a coset of codimension 1 in the space, what you could do is say, okay, I don't want to find the closest coset in dimension 1, but the closest coset of dimension 2. And the situation is now that one. So you have this wall lattice of dimension 3 lambda, you have a sublattice of dimension 1, and you want to cover the lattice lambda by copies of cosets of lambda 1, and these cosets are indexed by the quotient lambda over lambda 1. But this time, since lambda 1 is of dimension 1, lambda over lambda 1 is of dimension 2. And I will do exactly the same. So I take a target vector t, and what I do is now to find the coset of lambda 1 in the space lambda over lambda 1, which is the closest to t. And here it's also in green. And then once this is done, what I do is I project t over v plus lambda 1, and I recurse inside this coset. And the cost is now the cost of the recursion, solving it in the v plus coset v plus lambda 1, plus the cost of finding the closest coset, so an instance of CVP, but in dimension 2, which is a dimension of lambda over lambda 1. And from that, we get a direct generalization in arbitrary size, where instead of looking for the nearest plane or the nearest cospace of dimension 2, we directly look for the nearest cospace in dimension beta. And here we get this kind of algorithm, which is written not recursively, but in an iterative way. And so the first step would be to solve these CVP instances in the successive quotients that will index the blocks where we are doing the CVP, and we subtract the lifting of this value so that we can continue progressively. This is exactly the same structure as the nearest cospace algorithm in dimension 2, that is a bye-bye algorithm, where instead of solving small instances in dimension 1, we are solving small CVP instances in dimension beta. And the quality of the output will follow this kind of equation here. We will find a vector which is at distance at most the sum of the maximal distance at which we can decode on each of the successive quotient. And the time spent by this algorithm is polynomial multiplied by the time we take for solving these sequences of instance of CVP in rank beta. So all in all, we get a very neat generalization of bye-bye algorithms that will follow the same trade-off as BKZ. The problem is that with this formulation, we're a bit stuck with this formula here, because evaluating the quantity mu of the successive quotient is kind of difficult. To circumvent this fact, what we can do is to perform an average analysis. And in particular for a random lattice of rank n, we can prove that lambda 1 is greater than a certain absolute constant c multiplied by square root of n. And this implies that the covering radius is somewhat smaller than square root of n. And under this result, if we take a BKZ beta reduced basis, so an already slightly reduced basis, and that we suppose that every sublattice appearing during the computation of nearest colattice, then we can prove that we find a vector x which satisfies this inequality here on the retrieving bound. Okay, and the time is still the same, of course. This should be compared actually to the situation for the BKZ algorithm. And the BKZ algorithm find a vector which is within this bound theta beta to the n over 2 beta multiplied by the normalized covolume of the lattice in time, polynomial time, the oracle time for SVP in dimension beta. So we get exactly the same kind of trade-off for the same time complexity as we have for approx-CVP. And we can see here that we retrieve somehow the rule of thumb I told you earlier, because we need to first reduce by BKZ beta the wall basis in order to set up actually the blocks and to have sufficient restriction on them to be able to prove things on the governing radiuses. So what are the application of this kind of result? So first of all, CVP problem is actually ubiquitous in cryptanalysis, and we can see it in many places, and in particular for signature schemes following the so-called GPV framework. In this framework, a valid signature is nothing more than a lattice point which is close to a public target. And this public target is mainly the hash of the message we want to sign. Therefore, solving CVP in the lattice of the signature scheme results in making a forgery. In particular, our nearest-colattice algorithm allows to, once a reduced basis is found, to make batch forgery. Before that, we were using this cadence embedding technique to evaluate the security against forgery to these schemes a la GPV. And now, using this nearest cost space algorithm, nearest-colattice, we can prove that for the same cost as doing one forgery, actually we can do a big number of them. Batch forgery is now as hard as single forgery, which is an interesting result for practical perspective. Also, this algorithm can be used to analyze some trade-off in the primal attack against the LWE problem, so learning with error introduced by Regev, and it allows to use lattice reduction only once, this phase of BKZ beta, to amortize the cost of plugging it with combinatorial techniques such as guessing techniques or small enumeration, which is already used in some work of Albrecht and his collaborators. And in particular, this algorithm gives kind of framework that encompasses the amortization technique used in this case. So this is all for this short video, but I will be really happy to answer all of your questions in the question session, which is a bit later. Thank you very much.